Hello, yeah. In this video, I want to get into random forest using the random forest package. So it's still a video in the series of machine learning using R. So brief overview of random forest. Random forest is a simple learning method that combines many decision trees to improve predictions. It's actually uses a bootstrap as the core computational method. Okay. And each tree is built using a random subset of data and features, making the model robust and versatile. So it's pretty flexible. And has, like, I think, the built-in mechanism against overfitting. Predictions are made by averaging results from all trees, that's for regression, or using majority voting, that's for classification. Random forest handles the missing data well and provides measures of feature importance. Um, so it's very natural for handling missing data, and also the feature importance or variable importance is very useful for dimensionality reduction, such as you want to select the most important predictors among a large number of potential predictors. Okay? And it is widely used due to its simplicity, accuracy, and ability to work with large, complex data sets. Okay, so random forest is one of the most successfully developed statistical methods. It works well with many different types of data and with like excellent performance, like as good as any other machine learning algorithm. Okay. So it is really a very, very useful method. Okay. All right, I'm going to show you what the random forest package can do. We load in the package, set random seed, create a data set with dependent variable y and predictors x1, x2, x3. To fit a random forest model with importance and proximity, we use this syntax random forest where here the dot. So that means regress on all predictors. Data equal to data, entry equal to 500, importance equal to true, major proximity equal to true. So the n tree equal to 500 is the number of trees used for training as 500 trees. Importance is equal to true, means we ask R to return the variable importance measures. Proximity equal to true is we ask R to return the proximity matrix that measures similarities of the data points based on the forest construction. Okay. So it takes no time to fit the model, and if you print it out, it's down there. The model is printed out, it's pretty simple. You see the formula, and then the type of random forest is regression, and number of trees is 500. The number of trees, 500 is the default value of random forest package. You can change it using the entry equal to 1. Okay. If you get a smaller number of trees, then you get a simpler tree model, so that it can help with the computing speed and reduce overfitting, etc. Okay. And then the mean square residues for regression is also the out of bag error estimate, or the OOB error. So this is a measure of how well the model fit is. But now you only have one numbers, so without a comparison to another model, it's hard to say how hard to use this mean of square residuals. Okay, but we can look at the percent of variance explained. So this is sort of like the R square in linear regression. So here, the variance explained is 79.74. So that's pretty good. Okay. All right. So if you're wondering what's in this model object, so it actually much more information are in there. It's a list of 18. Okay. So you can explore each part of it if you're interested. So here I want to show you how to extract the variable importance. You just use the functional importance. And then you can print out the variable importance here. So you can see there are two columns. One is the percent increase in the mean square error. The other one is the increase in node purity. Okay. So the percent increase in MSE is the percent increase in mean square error due to the random permutation of that variable. And increasing node purity is increasing the total reduction in node impurity by splitting on that variable. Between the two, we usually prefer the increase in mean square error for predictive importance, and the increase in node purity is mostly measuring how often the variable was used in the tree building process. And for both measures, the higher the value, the more important the variable is. So here, if we look at this table, we find like x1 is the most important variable. Its increasing mean square is a little bit smaller than x3, but the increased node purity is much larger. So x1, x3 are equally important, but the measure of increasing mean square. Okay. All right, and also you can visualize this variable importance. So it look like that, and this is really like a demonstration data set. So we got 3 variables. So this is not very impressive, but if you have like 300 variables, this kind of variable importance plots become really informative. Okay. You may be surprised, maybe you only got a small number of predictors that's actually important. Okay. All right, we can also control the tree sizes by using the max node option. So this max node parameter is for controlling the maximum number of terminal nodes, leaf nodes, that each decision tree in the random forest can have. And if you specify smaller max node, lead to smaller trees. Okay, this is really if you want to reduce the complexity of the trees for various reasons, you can use this. Just random forest white here dot data equal to data max nodes equal to 10, and then you can see it's a similar output, but now if you look at the percent variance explained, it went down a little bit, but not by much. Okay. Also, random forest can be used for prediction, right? It's a predictive model, so we can use the predict function to generate all the predictions. So this is one prediction for predict the value for each data points. And for the proximity matrix, we can use it to actually do a multi-scaling analysis, MDS, by loading the library mass and do MDS, the scale, and then we can plot out this dimension MDS1, the first 2 coordinates. This plot showing the clustering of the data points, and we use the break equal to 3 to basically cut the y value, because it's continuous, into 3 groups. And then they are colored in different colors. And then point size is 19. So we can see how these data points are clustered. Don't be surprised that different colored points can be close to other points with different colors. Okay. So, but if you're really wondering which observations are these data points, you can use these command tags. MDS labels equal to row names of data, CEX equal to 0.7. So it actually tell you exactly which data point it is. Okay. In this MDS plot, I didn't see any like outliers. Sometimes it's helpful for us to spot outliers on here. Okay. But it seems like there's the 3 clusters, the data points. Okay. All right, more functions of random forest. We can use different number of trees by using n tree equal to 100 and m trie equal to 2. So m trie is the controls how many predictor variables are randomly sampled as candidates at each split. Okay. And then we can print out the summary. Okay, so we use the m trie equal to 2. It's actually the variance explained is 91%, much higher. But if you wonder which is the optimal m trie number, you can use the tone RF function to actually find the best M try number. So syntax tone RF execute the data, then which minus which is name, data equal to y, y equal to data at y, entry try equal to 500. And then we can actually print it out, and you can see here at 1 it's pretty large. This error is pretty large. O bear is 3.85, and then when m equal to m try equal to 2, it went down a lot to 1.48. Even if you go to m try equal to 3, it didn't go down a lot, which is 1.45. So it looks like the optimal m try value is 2, which we were lucky we just used it in the previous model fitting. Okay. All right. Also, if you want to uh, do some partial dependence plot, you can use keep the dot forest equal to true, and then you can use the partial plot function. So this is the partial dependent plot of the dependent variable on x1. So that tells you the individual partial dependence of the dependent variable on x1. And also you can use the library PDP to generate a similar partial dependent plot. Okay, another thing I want to show you is you can actually do random forest with weights. So here I'm just artificially create a random weight say for, we gave more weights to certain observations, which is larger than the median value of y. But you can have weights from other places, okay? But the syntax is if you do a weighted random forest, the same syntax, but there's a argument equal to weights equal to weights, okay? So this is another way you can implement the weights in random forest. Okay, thanks for watching, and if you like this video, please subscribe our learning channel and click on the notification button, and also recommend our video to other learners. Thank you very much.